Here in this example, we will see how to do the dropped object analysis. Okay, the following is an example of dropped object analysis using the dynamic response and collapse advanced to calculate the nonlinear behavior of the deck when object is dropped from a height above the deck. So, dropped object analysis for dynamic response. Dynamic response is the module, and collapse advanced is also in module in the SACS program. You will see the nonlinear behavior of the deck when object is dropped from a height. Means like when we drop some object, something like this, on this deck here, this location, then it will start vibrating. It will behave dynamically, so that we can see it here in this example. This figure 185 is the dropped object model, and it's a 1 centimeter deck plate. Here this deck plate is 10 mm is the deck plate thickness, and supported by 400 mm by 200 mm I-beams. If you see these I-beams, it's 400 depth by 200 wide, and with 5 mm web and 10 mm flange thickness, spaced at 1 meter. So the distance between these two is 1 meter. So this flange thickness is 10 mm and web thickness 5 mm. The beams have been meshed with a quadrilateral isotropic plate elements. All these plate elements, if you see, these are the isotropic plate elements to model the interaction between the beams and the deck plate more accurately, so that the between the beam and deck plate, so deck plate, it will be studying like this. So there will be a fillet weld here. If you see here, there will be a fillet weld at this location, at this location, and this is the deck plate and this is the beam. There will not be any gap. Just for clarity, I'm just putting it. Okay, a finer triangular plate mesh is modeled near the impact location. If you see here, this impact location, finer triangular plates are modeled. Impact location of the dropped object. A self-weight load has been applied to the structure. Self-weight, to the structure self-weight also applied. And the impact joint is 712, 4 meter by 4.4 meter by 0.0 meter. That the coordinate. That's the joint. Joint 712 somewhere here. There we are going to apply the impact load. So in this example, we can see how the dropped object is coming. We have to do two steps. One is extract mode shapes. Another one is dynamic response of dropped object with collapse. So we need to have two-step analysis. If first we need to extract the mode shapes. If you go to the extract mode shapes, we need to create the dynamic type analysis type, dynamic, and subtype extract mode shapes. Input file is the SACS model file only. Here you could see how the SACS model looks. Here this is the SACS model. What we have seen, that's a deck plate. Plate properties, if you see here, it's a 1 centimeter thickness and quadrilateral plates, and then here these are the triangular plates also modeled at fine-tuned locations, and joint 712. We have to find the joint 712. Here you could see the joint 712. This is the impact joint. So that joint we will apply the load. Here we can see the boundary conditions. Display labeling option, we can see joint boundary conditions. Here you see the boundary condition at the edge of the joints. Joint details. This is the joint fixity. 111 is the translation. Then torsion is arrested and major axis arrested, released, and minor axis arrested. So it can bend like this, but not in the plane direction. The same thing for here also. This is edge boundary conditions. Here you can see 0, 0, 2, 0, 0. That means in Z direction it is allowed to move. That's retained degrees of freedom. You can see the difference between retained degrees of freedom triangle and fixity triangle. Here you could see the retained degrees of freedom is triangle is like this: retained degrees of freedom, retained degrees of freedom, and this kind of symbol is for the fixities. So we are fixing 3 translation and rotation about global x-axis and y-axis and z-axis. This kind of fixity is given. So here in this model we could see the boundary conditions. Also you could see, and we can see the plate thickness of these triangular plates, especially at these intersection points where we have this loading and other one. Here these locations. Flange plate. Flange plate 10 mm thickness is provided. 10 mm thickness. We can see the plate element name also, and web thickness also we can see. Here is this web thickness. Web is 5 mm. On this flange location we have flange plate as well as this is the flange plate. That's a 10 thick, and then floor plate also it will be the, this is the floor plate 10 thick. So at this location we have the 2 plates. One is the flange plate, another one is the floor plate. We can see here by activating the, here you can see there are 2 items. You can see the 2 numbers here, ACE and ACMG, ACME, and one more below also. So, and how they are connected we can see it. For example, here this location, this flange plate connected with 961.1023 AAN1. That's a flange plate. Then here we can see the plate, that's 961.1023 AKKY. Here AAN1 1023.961 1023.961, but this joint C, that's different for floor plate as well as the flange plate. That difference we can see, and joint name also we can see it. There are here 2 different joints are there at the middle, because these 2 are not connected here together, but at this location it's connected, at this location it's connected. So what does it mean? That this floor plate is connected, this joint with flange plate. So it is like basically it will be welded kind of thing. If you see in the practically we have I-beam like this. This is the I-beam. On top of that we have the, you would be having the floor plate like this, and the floor plate and I-beam it will be welded here with continuous fillet weld. That's why joint 961, join 1023, it's connecting both flange plate as well as floor plate. Here there are two joints, one is for floor plate, one is for the flange plate. That's how it is modeled. So here we will see the load properties. And load, if you go, it's a self height of this member is applied, that's a dead weight. So each joint, these loads are calculated, the self height of the structure, it becomes almost 8 tons. So this much weight is applied as a self height case. And then if you go to this output file, we can see the PostView database, how the mode shapes are coming. Here we can see the mode shape. This is the deflection factor 1. For frequency mode 1, we will animate it. So this is the first mode, and if you go to the second mode, this is the second mode. For example, 15th mode, this is the 15th mode. We can see the mode extractions. And then we can go to this reports. We can see how the results are coming out. Here in the output list file, we can see how the results are there, the frequency analysis. So here we can see mode 1, mode 2, mode 3. And then eigenvalue analysis, frequency, period, all these things for the number of modes. It's almost 50 modes were extracted. So we can see the modes, and then weight and center of gravity also we can see. Here we can see the weight and center of gravity summary. Plate elements, that's weight is 81 kilonewton, it's there. And mass participation factor also we can see. From this output, here we can see the mass participation factor for each mode. This is the first mode, second mode, third mode, like that until 50 mode. Here it's a 74% vertical direction, 72% in the X directions. Cumulative factors we can see. Maximum deflections for mode shape also it's given. So once we know the mass participation factor and mode, dynamic modes and extracts like a period, this can be used for the subsequent steps. So next step, so this dyne mode, dyne mass, we can use it in the next step. That next step is nothing but dynamic response to dropped object with collapse. So here we can see in this extract mode shape the input file. One is the model file. Then next extract dynamic response. Here we have to go to dynamic type, analysis type and subtype, dropped object analysis, and SACS input is the model file, and dynamic response input, that's given here. So we can see this dynamic response input file. Here the line, this is a dropped object, dynamic dropped object analysis, and structural damping 2%, and load we are giving it, its object weight is 0.5 kips, and then here this is a free fall option, and this one is single impact, the impact joint, and distance before impact, that is 1.25 feet. This is the impact joint. So then time history, load, drop, that's the time history source, dynamic dropped object analysis, structural damping. These are the outputs we are selecting. First selection is the plot model response versus time, plot of overturning moment versus time, plot of base year versus time, print model response of all time points, create all load cases for all times. Then this is a joint, and how much time is starting time 0 second and end time 1 second with output time interval of 0.001 second. It will give the output interval, and these are the minimum integration time step, and default is 1.0 into e power minus 8, and integration control tolerance also is given here. This is how we can see the input file, dynamic response input file. Then extract mode save we have seen from the previous steps, and collapse input file we have to see here. This collapse input file, we are taking collapse option, and joint selection is 712, which load sequence means that the cell load case self we have given. Increment number of increments, only one increment, starting 20 factor 1.0 only, so it will make the collapse analysis. It will take all the loads in the self. So here collapse restart file will come. We can see the outputs, dynamic response OCI and dynamic response list also it will come here. So here in the list file, output listing file, we can see the displacements of each joint deflection report, load sequence increment, 465 load condition, load factor, like that. It can give a joint deflection report for this 712 joint. That particular joint, we can take the joint displacement report 14.5, 14.52. It will vary. The output we can see it here in the NPF file, neutral picture file, dynamic response we can see here. This is the output files. Even we can see it in the dynamic response file. Here this is the model responses for 0.5 second to 1 second. It's given here model response. Model is for each mode. So if you want to select first mode, this is the first mode response, model response. Overturning moment for first mode also we can see it here, base here, and then structure, object, contact, and object joint displacement. This is the joint displacement. Structure and object energy, this is the energy distribution. Displacement for joint 712, how it varies with respect to the time. Equivalent loads also we can see. This is the equivalent loads, moment, all this is we can see it. So we can see for all moments, model response for all moments. Overturning moment, how much it is coming, and base here also how much it's coming. We can see for each second it's varying up and down because of the dynamic nature. We can see the collapse log file. In the collapse log file, if you see it, not only a collapse analysis, load sequence, it's the loop self weight, that load case is self, and then after that it's starting with the impact load. Here we can see all this increment, load case, and load factor. Load factor we can see until 0.7, 0.8, 1.0, 1.0, like that. Load factor also is coming. Here we can see mode shape extraction. That first step we have performed, right, is performed to generate the dynamic model solution file, that is dynamic mode and dynamos. These two are dynamic model solution file using 50 modes. The dynamic responses use these files to calculate the dynamic loading on the structure. More information about the mode shape extraction theory can be found in the DynPack manual. There is separate DynPack is the module that we can see all this mode extraction analysis and theory. The following is the dynamic response input file. So this is the dynamic response input file to define the dynamic behavior. If you see SDAMP, the first line, DROPT line specifies the analysis options. Dropped object is performed DROP. From this DROP means the drop analysis. Structural damping is 2% is given. Load header line specifies that the loading data is to follow, because we are defining that loading header. Load, if we give it, that's a header, so that load is coming. Following next lines, the drop line defines the dropped object parameters. This line drop that defines the dropped object parameters. 0.45, the object weight 45 ton, okay, and is entered in column. That skips or a ton it's giving. The initial velocity is left blank, indicating 0 0, and columns 21 to 27, that is between somewhere here. And then the distance before the impact is 1.25. that distance also we are given, is entered in columns. The impact joint is given here. The adhere option, yes, here you can see, yes, adhere option will analyze the drop joint analysis a single impact in column. This is useful for instance where the structure does not remain elastic. If the structure remains elastic, it may be a bouncing impact, it will be there, but it does not remain elastic. In that cases, this is a single impact, that option is useful. The free fall option, O, will omit the object's free fall from the analysis. The next line is TH load drop. The TH load line defines the time history input parameters. So first load parameters drop, then next is time history parameters. The time history source, if you see it here, time history source is a drop, that is defined. This one, that is a damping is structural damping only, and various reporting options are entered. It is important to note that the CLP option indicates that dynamic response will create a collapse input file with the time history loads. All option indicates the dynamic response will create loads from all time points. So this one, it's important, this CLP, that CLP is nothing but that's it will create, dynamic response will create collapse input file with the time history loads. So then JTNUM, that's a joint number, no? That line selects 712 joint, reports if specified TH load line. The timeline specifies time integration control parameters starting from 0 seconds to ending with 1 seconds with input time interval of 0.001 seconds. That's here, this point, this time. That line specifies the time integration control parameters. This is the output, time interval output, and this ending second and starting second 0 0. This default these parameters and CLP line, that option indicates the dynamic response will create a collapse input file with the time history loads, and all option, here there is on all. This option indicates that dynamic response will create loads for all time points. The dropped object analysis will perform the dynamic response analysis and generate collapse input file. So here collapse input file will be generated during the dynamic response analysis using the loads generated at each time point. Generate a collapse analysis using the generated collapse input file. So once the dynamic response analysis is done, then it will generate the collapse input file for each time point. Loads will be generated, then using that loads collapse analysis will be done. So our collapse options parameters must be defined in partial input file. In a separate input file, we need to define the collapse options. The following is the partial collapse input file to define the collapse analysis behavior. So here, if you see CLPOPT line defines the collapse options. Maximum iterations is 20 per load increment is 20, and the number of segments, member segments, is 8, is defined in column 14 to 16. Arc length method for post buckling and sub incrementation to improve the convergence of selector. The deflection tolerance 0.01 and rotation tolerance 0.001 and member deflection tolerance 0.01 is entered in the columns, these columns. And strain hardening ratio, here you can see 0.005 is defined in columns. This value determines the plastic behavior of elements. collapse report line specifies the collapse reporting options. Here LADAPL line defines the first user generated load step. The load sequence ID is entered here, and the load case name we have given the self, that's the load case name. This must match the load case defined in SACS model file used for the collapse analysis. So this is important. This must match a load case defined in SACS model file used for collapse analysis. The number of increment is 1, starting factor 0 and ending factor 1.0. Then LAPC line associated input lines associated with time history steps are automatically generated and added by dynamic response. So LDAPC input line automatically generated lines associated with time history steps automatically generated and added by dynamic response. So we will see in the next figure 186 was the vertical displacement of the impact joint 712, and figure 187 188 is the plasticity at final load step. Torsional lateral buckling of support beam is clearly visible in figure. So this also we will see it. Here in this dynamic response dropped object collapse, we can see this DYR drop. Here it will develop automatically the loading file, collapse dynamic loading input file, and equivalent static model file. So here this is the collapse dynamic loading file. We can see this automatically it is created. So here we can see the joint is impact joint 712 LADPL. That's the load sequence ID is this one, and this is the load case name, and it's from starting factor 0 to 1 completely. That's the first load case, and second load case name is 2, and it starts from number of increments 1, starts from 0 to 1 with 0.5 second. Then third load case is this one, and number of increments 1, starting from factor 0 and ending factor 1, and time duration is 0.001. Like that it will continue until the load case of 498 load cases are continuing. This is the file automatically generated. That's a collapse dynamic loading input file. This figure 186 shows the vertical displacement of the impact joint 712. This is the vertical displacement of the impact joint. So deflection from 0 to -16. Then it goes up. Then it's going up and down for this load step. 600 load steps are there. Here in figure 187, XY top view of the plasticity contour at the last load step. These two figures illustrate the plasticity at final load step. The torsional lateral buckling, you can see this member, torsional lateral buckling of the support beam is clearly visible in this figure 188. There's a bottom view of the plasticity contour at the last load step. At the last load step, what is the plasticity contour? That's on this picture figure. And this lateral torsional buckling of the supporting beam is clearly visible.